In this episode, I'm going to show that Nash bargaining solution satisfies IID, independence of irrelevant alternatives. So once again, the Nash rule is given by an argument that maximizes this multiplication. What was IIA? Well, a bargaining rule F does satisfy IIA if for any two bargaining problem, SD, TD, don't forget the disagreement points are the same, such that the T is a subset of S. So the T is a smaller bargaining problem than D. And if the bargaining solution of bargaining problem S is in fact an element in set T, well then you know what? The bargaining solution of set S and T must be the same. If the bargaining rule satisfies this property, well then we say it satisfies IIA. Okay? So irrelevant alternatives are not important. So the rule F is independent of the irrelevant alternatives. Okay, so here, how do I show that the Nash bargaining solution satisfies this property? Well, it's simple, relatively. So I start with, take any. So this is the proof. So take any two bargaining problem, SD and TD, okay, with obviously T is subset of S. And then suppose, remember, I'm trying to prove if-then statement, so I assume this part. So conditional assumption, SD is in fact T. Okay, so what does that mean? Well, I'm using the Nash. So so my F, the bargaining rule is the Nash. So Nash SD is in T. Well, what does that mean? Well, remember the Nash solution is in fact an argument that maximizes this payoff, okay? So do I need to write it? No, not necessarily, but what is NTD? NTD is the following: argmax, where X is coming from individually rational set of payoffs in T, D, where I multiply I from 1 to n xi minus di. Okay? So what I want to say is the following. What is this set, individually rational payoff vectors in this bargaining problem TD? Well, this has to be a subset of individually set of rational payoffs in the set SD. Is that clear? Well, I mean, look, if a vector X is in ITD, it means xi is greater than or equal to di for every I, right? Well, don't forget, X is also in set S, and X satisfies this. So therefore, automatically, X is in ISD. So every element here is also in here. The converse is not necessarily true. So what does that mean? That means the Nash solution is maximizing this multiplication among all the payoff vectors, feasible payoff vectors in this set. Okay. Well, you know what? This point, NSD, is also here. So what is special about NSD? Well, NSD, because it's a Nash solution, is actually satisfying the following, is such that this multiplication, pi I from 1 to n, NISD, right, the ith guy's payoff minus his disagreement, and when I multiply this is greater than or equal to I from 1 to n xi minus di for any x, which is x1, xn in set S, in fact in ISD. Agree? So now I am looking for T, NTD. So NTD is going to be maximizing this multiplication. All right? Here actually, it maximizes this multiplication among all the payoff vectors, feasible and individually rational payoff vectors in this set. So what I know is that this set N, so let me ignore this. So NSD is in fact ITD, right? Meaning the Nash solution of the bargaining problem SD is in fact an individually rational payoff vector. So how do I know that? Well, I know that this is in T, right? Remember? So this is in T. And I know that it is individually rational. And in fact, it has to be individually rational in the set TD, right? I mean, it is in set T. It is individually rational for a larger set, so it must be individually rational for a smaller set, because individual rationality has nothing to do with being larger, smaller. It's all about whether this payoff vector is greater than or not from the disagreement point, and it is. All right, so therefore it must be an individually rational payoff vector. So therefore, and we know that this payoff vector, when I calculate this multiplication for this payoff vector, it's going to give us higher payoff than everything else in this set. So therefore, NSD must be the argmax, x in TD I from 1 to n, xi minus di, which is nothing but NTD. Okay? Once again, well, how did I deduct this? Well, I mean, simple. Remember, this payoff vector maximizes this multiplication, which basically means this multiplication takes higher value than this multiplication for any other x in the set. Now I am concerned about a smaller set. So basically this payoff vector beats every other payoff vector. All right, that's the idea. So the payoff vector beats every other payoff vector in this set. So this is like ISD, and this is ITD, and this is my payoff vector. So this payoff vector beats everything in this set, so it gives higher multiplication. Well, then obviously it should be giving higher multiplication than all the other payoff vectors in this set as well. So therefore, this payoff vector should be the solution to this problem. So it's equal to argmax. Well, why equal to? Well, because remember we said the Nash solution always leads to a unique prediction, a unique solution. So therefore it's not element, it's equal to. Well, this argmax problem is nothing but the Nash solution for the bargaining problem TD. And hence the SD, the bargaining solution, the Nash bargaining solution for bargaining problem S and T must be the same as we requested. All right, so we didn't prove it by contradiction. This is a direct proof, but this is exactly how we prove that the Nash rule satisfies IIA. I hope that was clear.